Good morning, good afternoon, everyone. It's the 21st of April, 2025, and today we're very happy to have Liam Egan at the Owen Labs Crypto Seminar. So a small reminder before we start, the duration of the talk is 1 hour, and if you have any questions during the talk, please feel free to ask them, raise your hand, or maybe if the speaker gives a bit of time. So it's usually better to ask questions along the way and not leave them to the end, because that's the one thing. If you want to use chat, you can use the chat, but if you can speak up, that's significantly better. And we do have a Notion page and a mailing list. So to join the seminars, I didn't even advertise this one on Twitter and Discord, because I feel like not many people join from these. It's primarily engineers, so this is mostly attractive to researchers. But a lot of people join the mailing list now, so mailing list is growing a bit. I think mailing list is primarily attended and followed by researchers. That's a good place to go and subscribe if you want to get notifications about future events. And I think this is a crowd that I'm trying to target more. So yes, Liam, thanks for coming. Liam is a cryptographic researcher focusing on applied snarks, worked before on lookup arguments for linear schemes, techniques for elliptic curve operations. Liam is also a founding cryptographer at the Alpine Labs company, where he's working on verifying snarks on Bitcoin. And today, Liam will be giving a talk together. There's a recent work that was done together with Ariel Gabazon, right, on Mercury, the Multilinear Polynomial Commitment Scheme. So yeah, thank you all, Liam, for coming. And
thanks. Yeah, so that's my intro. I'll just get right into it. Yeah, this is also joint work with Ariel. So yeah. So I will start with a little bit of a high level, because I'm not sure what everybody's background is, but like this is about a multilinear polynomial commitment scheme. So for those of you who know, this is going to be very much related to sort of sum check based snarks. Then I'll describe our results and sort of contextualize them in the space of existing multilinear polynomial commitment schemes, and sort of describe those in a little bit more detail, because Mercury is sort of, in a certain sense, like a hybrid of two existing multilinear polynomial commitment schemes. And yeah, so there's this existing trade-off basically between the existing KCG-based multilinear polynomial commitment schemes. They sort of either require constant size, or they require doing kind of linear sized FFTs, which take n log n time, and then you can have a constant proof size, or you can have a log proof size with sort of O of n field work. So a minor note I just want to get out of the way now. I'll try to be specific or correct about this, but sort of you could think of this as like linear time. It's not strictly speaking linear time, because all of these schemes that I'll be talking about now use elliptic curves and sort of like KZG commitments. And even if you're committing to a linear sized vector with KZG, that doesn't take linear times, kind of subtle arguments about this, but you can sort of think about it, at least in the context of elliptic curve based snarks, as being linear time. So all of that being said, you either have the log size proofs and log size verifier work, or prover FFTs. And Mercury, we're able to get the best of both worlds. No big prover FFTs and constant size proofs. So then I have some additional information at the end that Mercury is sort of related, although not exactly the same as like a bivariate sum check. And it's also worth mentioning that almost immediately after the publication of Mercury, there was a concurrent work called Samaritan that has a substantially similar scheme which is I don't actually recall if they describe it as a bivariate sum check, but it is a bivariate kind of scheme. There's a natural way in which that'll probably make sense when we get into it. Okay, so yeah, sum check protocol, really great protocol. If you haven't heard about it, you should definitely check it out. It's used in all kinds of snarks, Spartan, Hyperplonk, Honk, basefold, all kinds of stuff. And the reason for this is that it allows us to have linear time provers, as opposed to older schemes that tended to use univariate polynomials. When you use univariate polynomials, you oftentimes need to perform FFTs. So using sum check by itself doesn't guarantee that you'll have a linear time snark, but it does save a lot of prover FFTs. But in order to construct a snark using sum check, we need to evaluate different type of polynomials. So here I'm assuming some background with snarks, right? Univariate is like a polynomial in one variable, and so when you construct a snark out of univariate polynomials like Plonk, you only need to evaluate sort of these common polynomials with one variable that we're probably all familiar with. But for sum check based snarks, we need to evaluate multilinear polynomials, which have kind of log variables, and each variable is of at most degree 1. And in any case, we need a new type of polynomial commitment scheme to go from a multilinear IOP to a multilinear snark. So just to describe the Mercury results briefly, the existing schemes for KZG required this trade-off I was talking about. You either have to do kind of univariate style FFT to compute a quotient, and then you get a constant size proof, or you use log n rounds to get ON time. And by ON time, I mean linear fieldwork and O of n MSM. In Mercury, we get the best of both. We have the same notion of linear time and constant size proofs. So yeah, this is, I sort of said this twice, but this is what Mercury gets us. There are a number of other sort of practical benefits, like a reduced verifier work because it's a constant size proof. In fact, it's actually less prover work than other linear time KZG-based MLPCS. So these are just basically definitions for sum check, so we're all on the same page. We have multilinear functions, degree 1 in each variable. The multilinear extension of some values is unique multilinear function interpolating those values. So if you've seen Plonk, right, you have univariate functions interpolate using the Lagranges. And in the multilinear case, we have these weird looking functions that you can think of like the multilinear Lagranges. They're called the EQ functions. And every multilinear extension can be written using the EQ functions. And these EQ functions have this nice property that they're kind of like diagonal, basically. When you have two arguments, A and B, that are taken from their domain, which here is just like we call the Boolean hypercube, it's just like bit vectors. When the two inputs differ, then one of these factors vanishes, and so the whole EQ function vanishes. So they equal 0 if A and B are different, and if they're the same, then they equal 1. And we can write every multilinear extension using the EQ functions. So all of this is probably pretty familiar if you've seen sum check-based snarks before. These sorts of tricks show up all the time, but a little bit be more esoteric than the univariate stuff. Yeah, so a multilinear polynomial commitment scheme is similarly to a univariate polynomial commitment scheme, a way for a prover to prove that some multilinear extension, when you evaluate it at any challenge point u, where u here is like a vector, you obtain some prescribed result v. So we're proving that when you evaluate f hat at u, you get v. Wait, I think I caught. Let's see. Okay, yeah. I don't know what's going on with this slide, but maybe I moved it around wrong. Anyway, yeah, so we have this trade-off we were talking about. Basically, like of the two schemes, we usually tend to go with the ones that have O of n prover work, because the whole point of doing sum check was to avoid FFTs. Right, FFTs show up when we have univariates. We move to sum check, we get rid of FFTs. So if we use this constant size MLPCS, we'd just be reintroducing FFTs. So like not super interesting. And I don't actually know how well. I know at least at Aztec they use Gemini, which is one of these O of n prover work MLPCSs. Another factor that I sort of mentioned earlier is that Gemini, which is or like a variant of Gemini that Aztec uses, requires 3n scalar mols for each MLPCS opening. So if you're familiar with the KZG scheme for univariates, it only requires n scalar multiplications for a single opening group. And 3n is quite a bit more than n. There is another scheme called Zeromorph, which does a little bit better than Gemini, but still it's higher than KCG. With Mercury, we're able to get it down to 2n, with this additional caveat that I don't have written here, but I don't know if this is a little in the weeds, but all these numbers are for the sort of standard KZG pairings. So when you have a KZG trusted setup, you have your powers of tau in G1, and then in G2 you'd have like 1 and tau. So this 3n, 2.5n, and then 2n for Mercury are all with instantiations using only those two standard KZG pairings with 1 and tau. If you allowed for 3 pairings, Mercury actually has the same cost as KZG. But unfortunately, most KZG trusted setups don't have extra G2 elements. So I don't know if that's interesting. Yeah. So right, MLPCS, as I said before, we want to prove that when you evaluate an MLE, you get some value. This is how the constant size MLPCSs work, and it'll sort of show up in the definition of Mercury. Basically, you just take your definition of a multilinear extension, right, as a sum with these EQ functions and the evaluations on the Boolean hypercube. And then this sum check, if you will, we can instantiate it using a number of different univariate protocols because it's just a degree 2 sum check. So there are actually several different univariate protocols for degree 2 sum checks. We use a specific one in Mercury that I have a slide for at the end, but it's a bit in the weeds. But yeah, so you can use the Aurora sum check, which if you've seen, basically when you have your univariates defined over the standard roots of unity Lagranges, you can just evaluate at 0 and it will give you the sum of the values up to constant factor. You can also use the kind of partial sums thing. But anyway, all of these protocols, because it's a degree 2 sum check, will require computing FFTs. So there's also a nice trick where, like, yes.
Oh, sorry, I actually thought you finished the slide. I'll ask a question anyway. So by degree 2, you mean the degree of the equations involved? So what is the degree of the EC? I always forget. Is it 2 on itself?
So the way I would think about it is because the EQ is like partially evaluated on B, it's like degree. So there's few ways you could think about it. Like, or I should say, it's evaluated on you.
Mhm.
It's degree 2 in each of the like B's. So like the first B, B1, it'll be degree 2 in that. In B2, it'll be degree 2. So it's not multilinear, it'd be like multi-quadratic or something like that. But what I mean here by a degree 2 sum check is actually just that this inner expression, if you take the EQ function as like one degree 1 object and the f hat function as a degree 1 object, then the sum is degree 2 because it's just a sum
I
of
see what you mean.
products.
Okay, I see what you mean.
Yeah.
Okay, thank you.
Yeah, and the way that we encode the f hats, which I'll describe with Gemini, because it's the same, you can actually get like the EQ encoding, it plays very nicely with it, basically, because they both will decompose kind of in this tensory sort of way. But it's a little vague, I guess. Okay, so the constant size MLPCSs, we can just sort of black box for now, and say, like, we have a bunch of different degree 2 sum check univariate protocols, and we could use any of them. They'll all be constant size. They'll all require computing an FFT, at least one FFT. But that's okay. We can still make use of this. So now, how do the linear time MLPCSs work? So these are the ones that don't require uh, FFTs, but have the log proof size. So we're going to focus on Gemini. Zeromorph is fairly similar, at least in terms of structure. So again, we have our MLE, or MLE of like a multilinear function. The way that we encode it as a univariate is in the coefficient form. So here we're like summing over the B's in the kind of like lexicographical order. So like the vector of all zeros would come first, and then like 1 and all zeros, and then like 0, 1 and all zeros, and so on. It's sort of like binary counting. And so then we can treat each of these bit vectors as like an integer by sort of summing with powers of 2, and then that goes in the exponent. So each evaluation has a different x monomial, and they just basically unroll as the coefficients of this univariate f. So you write f hat for the MLE and f for the univariate. This is the same encoding that I mean, it depends actually on like which scheme you use, but for us, it's the same encoding as the FFT based, degree 2 sum check. So the kind of trick of Gemini is we can relate evaluation claims about this univariate polynomial f to the evaluation claim that we care about for f hat. And so for the univariate evaluation claims, we can use a univariate PCS, like KZG, for example. And if all these univariate evaluation claims are satisfied, then we want the final claim about the MLE to be satisfied. So that's the structure, and I'll describe in more detail how this works on the next slide. Right, so it's the same MLE evaluation we've been talking about this whole time, right? U is a vector, has k variables. So we can define the partial evaluations of the MLE. These are basically what they sound like. You just sort of substitute in the first I variables with your evaluation point. So F1 would just have U1, F2 would have U1 and U2, and so on. So each of these MLEs is going to have one fewer variable and half as many terms. And to each of these partially evaluated MLEs, there's also a corresponding univariate. It's the same encoding as before. And then each of these will have 1/2 the degree of the previous one. So f1 will have 1/2 the degree of f, or you can think of it as like f0, and f2 will have 1/2 the degree of f1, and so on. So then fk will have degree 0, I think, or 1. I may have screwed the algebra up there, but anyway, you fold it down to a constant. Yeah. So this is the Gemini identity, the trick that we use. The algebra is not too bad, but it's a little much for the slides, I think. So basically, you can, when you write out the evaluations of the MLE as coefficients, as we have, then you find that if you sort of like were to evaluate the MLE at 0, you would get the even coefficients. And if you were evaluate the MLE at 1 in the first variable, you'd get the odd coefficients. So when you evaluate it at u, or u1, you end up taking a linear combination of the even coefficients and the odd coefficients. And this makes some sense, right? Because when you partially evaluate the MLE, you reduce the number of terms by half. And you reduce the number of terms by half in like a very structured way. You kind of, depending on the ordering of everything, you basically take adjacent terms and you combine them because you've eliminated one variable. And that's exactly what we do here. So this is explicitly how it works. And then the crucial bit here is that fi even, that is the even coefficients of fi, are related to the coefficients of fi. There's this very common identity. It shows up all the time in Fry and elsewhere, where the even coefficients of fi are just sort of fi of x plus fi of negative x. And this causes all the odd powers to cancel, and then you're left with fi even evaluated at x squared. And you can do the same trick for fi odd by subtracting the two, and then potentially dividing out by x. So the point is that we can compute fi even and fi odd from evaluations of fi. And we can relate them to then an evaluation of fi plus 1, which is like the subsequent partial evaluation. And in this way, we can link evaluations of fi to evaluations of fi plus 1. And notice there's a squared in here. That comes from the algebra. And so the rest of Gemini basically just follows from applying this log times. Yes.
Yeah, I just wanted to ask. So, what's the direction of dependence? This is the same. This is the same basic like algebraic relation that is, as you mentioned, used in Fry and in FFTs themselves. I think, if I'm not mistaken. Right, so you just kind of draw a line, and then there is a expression of the even powers or odd powers for the square inside. But like, what is the direction in which we progress? Like, do you compute them like from the 1 index to the k, or the other way around?
Yeah. So like f1 has
From the end
2
phrase.
to the k minus 1 terms. So I think it makes more sense to think of the foldings as increasing the indices, as I've written it here. So like you'd go from f1 to f2. So like f1 of r and f1 of negative r gives you f2 of r squared. And then is that what you're asking?
Yeah, but I'm kind of thinking that it should be the other way around. No, first you kind of do the full evaluation, or it's so you. I guess like chronologically in terms of the protocol, you progress, like you said, right? But the first actual evaluation you get only in the end when you instantiate all the variables with some concrete field elements, right? And then you can kind of relay them back.
Yeah. Well, I mean, you have the whole evaluation point at the start, right? Like the U1 through UK are given as an input to the protocol.
Okay, I see.
So,
Yes, exactly. Yeah.
yeah. It is in that way. It's like different from Fry, where you'd like sample each subsequent U1 with like the foldings. Like you don't know the whole point ahead of time. But yeah,
Okay,
here you could go in either direction, I think.
Okay, that makes sense. Yeah.
Okay. Okay, so now Mercury. Yeah, so this is the kind of high level of Mercury. In Gemini, as we just saw, you always fold by a factor of 2. You take even and the odd coefficients and you fold them. If you've seen Fry though, like a lot of practical or like real world instantiations of Fry, do the same thing, right? They fold, but they fold by a factor greater than 2. So, if we could fold by a factor greater than 2, as we do concretely in a lot of Fry instantiations, we can use fewer rounds. So if we folded by a factor of 4, say, we would use half as many rounds. If we take that all the way to the extreme, if we folded by or I should say generically, if we fold by a factor of b, then it will take us log base b of n rounds. So setting b to be like square root of n, it would only take 2 rounds. You'd fold by a factor of square root n once, and then you'd fold by a factor of square root n again, and you'd be done. There are protocols that sort of give an. I'll talk about the specifics of Flonk in a minute, but like they sort of have the shape that we want, right? And this folding by a factor of 2 with the even and odd coefficients generalizes really nicely in an FFT kind of way to any k. However, like Flonk, for example, which is a protocol that does that explicitly, requires sending O of k like evaluations, basically k evaluations. In the same way that before, right, we had the evaluations at r and negative r, so we'd have to send 2 evaluations when we're folding by a factor of 2. This is a problem. If we wanted to fold by a super constant factor, then the protocol is going to have super constant size. You fold it by a factor of square root n, and you send square root n evaluations, then the proof size would be square root n. That's not good. So it turns out we can improve Flonk to send a constant amount of information and fold by any k. So instead of sending k evaluations, what we're going to end up doing is sending a polynomial that encodes these k evaluations, a polynomial commitment. And we can relate this polynomial commitment to the polynomial that we're folding and construct a proof of that in linear time. Again, linear time here meaning like O of n MSM and no FFTs. So yeah, this is sort of the crucial step, the ability that we can fold by any k and keep our O of 1 sort of proof size and linear time. And once we have that building block, we can sort of just do Gemini with 2 rounds, if you will. We can fold by a factor squared n, send constant information, and then we can use the n log n inner product degree 2 sum check based MLPCS. And this, so even though that MLPCS has like n log n running time, we're only using it on a vector of size squared n, which is much less than O of n, and we maintain overall linear running time. This kind of trick is also fairly common, although I think sometimes underappreciated. In fact, you can sort of, there's a parameter here basically, where here I'm saying we fold by a factor squared n and we fold by a factor squared n. But you could imagine we fold by a factor b, and then we fold by a factor n over b. And that b can be as small as log n, and we would still have a linear time prover. And this is because like n log n applied to m over log m, where n equals m over log m, will give you O of m running time. So anyway, yeah, a bit of a digression there. But in our case, the optimal thing to do is to just fold by a factor squared n. Yeah, and so once we have all this, that's yes.
Yeah, sorry. I wanted to ask a short question about the, I guess, point number 4 here. So, just to recap. So here you're talking about the increasing the amount of these like sub polynomials instead of sending the odd and the even simulations for the odd and the even. You kind of increase the spacing between the elements, and you send like more sparse polynomials. I guess is that the idea?
Yeah, it's like if you have odd and even, you can generalize it to like every kth coefficient.
Yeah.
And so I suppose in that sense they're more sparse. And then we want to work with all k of them at the same time, but not have to like send k information or k evaluations.
Yeah, I was wondering how, like, I think you mentioned this, but do you have a slide for how it would work in a more naive way? So in the previous slide, you would send the evaluation point and the minus evaluation point, and I just kind of know that with the r and minus r it works. I'm convinced that it works, but I don't have any intuition of what it would look like when you generalize it. So would you have to send like roots of the same filled element, or just like additive roots? Like just how would the evaluation point look like?
Yeah, I think the next slide has this.
Perfect. Okay.
But yeah, right. Like you can think of r and negative r as just like r times 1 and r times -1, where 1 and -1 are the two order 2 roots of unity, and we generalize that to like any kth root of unity. Which, if I'm okay, yeah, I think this slide should have it.
Yeah. Okay. Perfect. That's what I was asking. Thank you.
Nice. So yeah, in Gemini, fold by factor 2. This is our relation from before. We can say f of x is the even polynomial evaluated x squared plus x times the odd one. So yeah, the flonk kind of identity, which is what we're talking about now, where we generalize from 2 to k, works like this. We take some primitive kth root of unity, and so like if it helps, like you can imagine omega here is -1 and k is 2, and we will arrive at exactly the original identity. And we can write the k-fold FFT decomposition, which it's just like it's also sort of what the FFT uses internally to do its thing. At least the Cooley-Tukey, like the power 2 FFT. Yeah, so we go to get these like sub polynomials, as like we were talking about, that are sparser. They like every like the first coefficient goes in the first one, second coefficient, the second one, up to the like the k-1th coefficient, and then the kth coefficient will also go in the first one, and so on. So they'll have spacing of size k, and you multiply each one by a different power of x that's like less than degree k. So it should be not super surprised. Like if you can check out the algebra that this will like have each monomial show up exactly once. It's sort of like each n mod k basically, where I is the residue and then this encodes the quotient bit. So the way that we generalize the folding by a factor 2 to folding by a factor k uses the FFT matrix actually. So what we're going to do is relate these like kth roots of unity times r to the subpolynomials evaluated at r to the k. And so what we're going to do is like if we substitute in omega jr into this equation, into the definition of f, all of the fi's are evaluated on x to the k. And so as we saw, omega to the k equals 1. So that means this first factor in the sum will always become f sub I evaluated at r to the k. And then the first factor, yes?
Oh, yeah, it's mostly a comment, or maybe yes, a question. So I it looks like it's like the generation of the FFT when we have the subgroup that is not only a power of 2. So here also we've got to change the subgroup that we work on, the subgroup of the field, right? Like it has to, yeah. So we've got to take like I don't know if bigger, like for the field using the pasta curve, for instance. I think there is a coefficient of 3 and 5, something like this. So we can reduce the fold by as much as big the factor k is in the decomposition of the field. If
yeah.
And I feel it's like the generalization of the FFT, not the generalization, sorry, but like a link with how you generalize FFT when you don't only have roots of unity with a power of 2, but like you've got also like Kulitaki with like 3 or 5 or any prime. Does it make sense to think it like this?
Yeah, absolutely. I think that's great. It's also a good point that, like I say, we have this omega k where the omega to the k equals 1. I think that, to your point, this is assuming that k divides the characteristic of the field minus 1. Or I mean, we're in a prime field, right? Because we're working with elliptic curves. But so, yeah, like for omega to exist, we have to have k divide p minus 1. And yeah, this is absolutely the same kind of decomposition for generalized FFTs with radix other than 2. Yeah.
Okay, thanks.
I think as just a practical note, in most of the elliptic curves that people use in practice, specifically BN and BLS, since we're working with KZG, there are large power of 2 subgroups because people want to do FFTs for univariate snarks. So it's not true in general, but in practice for those 2 curves, you can always pick K to be a power of 2. So just worth noting that. Yeah, so just to finish this off, relating these evaluations to the evaluations of the subpolynomials. This shouldn't be a comma. It's like a multiplication. So this is the DFT matrix. This Mij is just omega raised to the I times j. And we can write this is the vector of evaluations of f at like essentially a coset indexed by r as being equal to the FFT matrix times x to the I times fi x k. So yeah, this is sort of taking advantage of the fact that when you plug in omega to the j into x to the k, you always get 1. So like this stays the same, and you get like a different root of unity linear combination of these terms in this vector for each evaluation point. And it's precisely encoded by the DFT matrix M. So if we wanted to go in the other direction and calculate fi x to the k from a bunch of evaluations, which is what we do with the even and odd polynomials, we calculate them from evaluations of f. We would take all these evaluations, all k of them, and then multiply them by the inverse of the DFT matrix, which itself is also a rescaled DFT matrix. So that would take n log n time. And then we just have to deal with this constant factor scaling by x, which is no problem. That's just a linear time operation. And that lets us write the evaluations of the subpolynomials in terms of the evaluations of f on the coset. So that's how it generalizes from 2 to k. Right. So naively, we'd have to send k evaluations, right? This vector has k terms in it. And actually, it would require k log k time to like work with everything, which in our case isn't a problem, but ideally would be best to avoid. So the trick that we use in Mercury for avoiding this extra communication is to transform the statement that we care about into a relation of univariate polynomials. So in particular, we're going to reduce f, the f from before, mod x to the k minus r to the k. So substituting all of this, we have our original f, which as before was just the x to the I times fi x to the k. When we reduce this mod x to the k minus r to the k, we can replace each of these x to the k's with r to the k. And this reduces the degree of f, or the g, I should say, right? The reduction of f mod this polynomial will have degree k minus 1. And so why does this work? Well, I mean, you can sort of see how we get the same result, or at least we get the things we care about as the coefficients of g. But like, why does this work? Well, every time we evaluate this whole identity on omega to the jr, the kind of vanishing polynomial, or the thing we're reducing by, vanishes, right? Omega to the j times r are precisely the roots of x to the k minus r to the k, because omega is a kth primitive root of unity. And because of that, if we were to write this out in like the quotient form, it would be g of x equals f of x minus or plus this expression times some quotient. And so this expression vanishes, the thing we're reducing by. So we're left with that g omega to the jr equals f omega to the jr. So g agrees with the evaluations of f on the coset. And this in general like works for univariate identities. When you have like a bunch of points that you want to evaluate a univariate at, you can reduce it mod the product of those points, or the polynomial whose roots are the points that you would like to evaluate at. And it preserves the evaluations of the larger polynomial at those points, which is what we're doing here. And there are some like nice little like conveniences, I suppose, of this approach. It no longer like is conveniently expressible like in terms of the roots, but if we just replaced r to the k with anything, then we would be able to evaluate the FIs at anything. All the algebra here will work out. If you were to sort of factor the thing you're reducing by, you'd need to move to an extension field, so it's a bit messy. But it's no longer the case that r to the k actually needs to be a kth residue. It could be any point. And this g and the associated quotient for this identity can both be computed in linear time. As a sketch of like why, we go through it in the paper, but you can sort of think of it as you take each of these chunk polynomials, the f sub i's, and you apply a normal univariate evaluation or quotienting kind of operation, which runs in linear time. And then you can take these, and because each of these is sort of shifted, you just sort of can take the quotients and then shift them and add them together. And that allows you to compute the quotient in linear time. So, yes.
I guess my question actually was regarding the last part, but that seems to be a very important point here, right? So instead of evaluating the equation normally, you first like shrink it to the exactly the points which you care about, But I guess the fact that you can shrink it to the sub-equation is not exactly obvious. So also, am I right that R is the original point at which we're doing the evaluation?
Yeah.
I kind of lost track of notation. Okay, so that makes sense. So you need to do this reduction only once per evaluation, right? So you do it only once per whole protocol session.
We only do this once because we only fold once. Like we fold by a factor squared n and then fold by another factor squared. But the second folding is different. It's like the last step. But if you were to apply this to like Gemini with a larger radix, you would apply this every round instead of sending the even and odd evaluations.
Exactly. Yeah. I guess that's what my point was. So you only need to do it like twice, and you say once because the second phase you also optimize for that.
Yeah.
Which is why it's fine. So you do like a constant time linear in your reductions of G.
Yeah. Yeah. Exactly.
Perfect.
Yeah. All right. So this is, I think, the main sort of point. A lot of the rest of it will follow just from fleshing out the details, basically, of how to use this to replace the rounds of Gemini. So this point is a little poorly written, but it's basically the idea is that as we saw with Gemini, you have this sort of U1 through UK. This is also very confusing notation, but basically you can split your evaluation point. So like we could evaluate it at the first coordinate only, or we could evaluate at the first two coordinates only. So what I mean here is that you can evaluate at like the first half of the evaluation point. So it'd be like U1 through UK over 2. And then the second half is going to be UK over 2 plus 1 up to UK. And that's what U1 and U2 are. So what we're going to do for Mercury is commit to the partial evaluation defined in the like previous Gemini sense at the first half of U, like the first half of the evaluation point. And so the kind of point of the tensor product structure is we commit to the first partial evaluation by half of the evaluation point, and then we take f and we fold it by a factor squared n. And it turns out that in much the same way that Gemini relates like foldings by factors of 2, we can sort of relate this folding by a factor squared n to the partial evaluation. I think this is clear, and that's on the next slide in like math than it is in words. But it does kind of depend fundamentally on this tensor product structure. It's also why this protocol does not, for example, generalize to inner products. Because right, like an MLE, like an MLPCS is very similar to an inner product protocol. You're taking, like as we saw before, an inner product of like these EQ functions with some evaluations. But this EQ function vector has very nice structure. And if it didn't, then this protocol wouldn't work. So yeah, we fold by factor squared n, and then we can use an inner product protocol, which is like the n log n time protocol I described earlier, to link the folding with the committed partial evaluation. And then we can use another inner product protocol to finish the partial evaluation. So each step in this process is constant size and linear time. The folding, constant size, linear time. The inner product protocol, constant size, and actually square root, log, square root, and time, which is linear or sublinear. And likewise, the second inner product, also sublinear. So we're doing a constant number of steps. Each step is linear or sublinear, and each step requires sending constant information. So overall, the protocol will be constant size and linear time. So this is the protocol in all of its, well, not all of it, but much of its detail. There's a bunch of stuff in the paper for like steps 8 and 9 for kind of like how to KCG golf this down into like a, smaller size. You can kind of combine different checks and whatnot, and familiar, maybe you've seen like these kinds of protocols before, but right. So we define B to be square root n. It's worth noting that, like I think I said this before, but B doesn't have to be like exactly square root n. It could be like 2 square root n or 1/2 square root n, depending on like the constants involved. It might make more sense to use like a slightly larger folding initially or a slightly smaller folding initially, if you were to use a similar kind of trick in a different protocol. In fact, it doesn't even have to be asymptotically square root n. It could be, anything. So we define our f, or we define the chunks of f as we did before. So this used to be k, but here I write b. We split our evaluation point in half into u prime and u prime prime. And then we commit to the partial evaluation. So if you were to work out the algebra from Gemini, this is the partial evaluation of f, or f hat, at u prime. So we get all these EQ functions times these chunks. And actually, also another minor technical point. Here we're assuming that b is a power of 2, like exactly a power of 2, in order for everything to sort of align. So it should say something like O of square root n or something like that, and it's a power of 2. Yeah, so we commit to the partial evaluation at half of the evaluation point. We choose a random challenge, alpha, and then we commit to this g, which, as we see here, is congruent to f mod x to the b minus alpha. So here I use the trick from before I was talking about, where instead of it being like r to the k, it's just any alpha. And so we commit to g, we commit to q as well, and we commit to h, that is the partial evaluation at alpha. So if we take the inner product of g with the vector of EQ evaluations on the first half of the evaluation point, this should give us exactly h of alpha if h is correctly constructed. We assume g is correctly constructed because we can check this univariate identity directly. And you can sort of see in one direction, like g is like x to the I times f sub I evaluated at alpha for all I, the sum of it. So if we take an inner product with an appropriately defined EQ vector encoded in the right way, this will give us EQ u prime I times fi of alpha. Similarly, if we evaluate h at alpha, we'll get EQ u prime I times fi of alpha. So these should agree if you work out the algebra. And then the final step, we just do another inner product protocol on h to finish evaluating it. And both of these inner products are of size square root n. So this is exactly the kind of thing I described on the last slide. These final 3 points, or I guess not final, but the fold by a factor square root n, do an inner product, do a second inner product. That's basically what's going on here with step 7, 8, and 9. And that is all. I have like other stuff, but I think that's basically time. So yeah, thanks.
Yeah, thank you a lot, Liam. I think it is basically time. You finished exactly on the second. I think we can leave space for a few questions and wrap up maybe in a few minutes.
Yep.
If someone wants to ask a question, yeah.
Hi, thanks for the great talk. Just a very minor question. At the very beginning, you mentioned that KCG is not does not require linear time. Did you just mean that the what is it called, the MSM is actually below linear time? Or I wasn't sure what you were hinting at the very
Oh,
beginning of the talk.
yes. Yeah. So the right. So an MSM of size n can be done with Pippinger's algorithm, which takes n over log n group additions, or like elliptic curve point additions. Each elliptic curve point addition takes like at least O of lambda, or I should say it takes n times lambda, where lambda is like the security parameter, divided by log n point additions. And each of those point additions takes O of lambda time. So overall, we're at something like n lambda squared over log n. And the argument is that in order for n to be negligible, log n has to be smaller than lambda. Like concretely, lambda is going to be like 128. So log n obviously has to be smaller than 128. So people say that like n lambda squared over log n is superlinear in n.
Oh, okay, get it. So that's why it's even technically like in practice worse than just being linear. Okay, thank you.
Yeah. I mean, I think this is like a more recent development because there now actually are like snarks that are sort of in some sense properly linear time, like that don't have this extra lambda factor, like some of the code-based snarks.
Dan, you want to go?
Yeah, sure. So I've got two questions. The first one is more on the practical side. So we haven't moved to multilinear polynomials at the moment in some checks, because first we haven't investigated that much yet. But also, I'm wondering on the practical side, the other projects, how many variables do you have in general? And what's the domain size that you use? And why I'm asking that is because always here you divide you fall by a certain factor, which is depending on the number of variables. And so I'm wondering in concrete case, what are exactly the values? Is it 16, 20? And if it's 20, which factor do you use, etc.
Sure. So they're I mean, I can't speak for all projects, but I think we're using multilinear polynomials, so the domain looks like kind of like a power of 2. So if your column size is 2 to the 20, you would have 20 variables. And if your column size is like between 2 to the 19 and 2 to the 20, round up 2 to the 20. It's pretty similar to, I think, if you use univariates, you're usually going to pick a power of 2 size subgroup. Maybe not always, but I think this is pretty common. So then, in terms of like how do we factor it? I think to make everything nice, we're assuming that you basically have an even number of variables. So if it's 2 to the 20, we're assuming that you have 20 variables, and you sort of split them into the first 10 variables and the second 10 variables for Mercury. For Gemini, they don't have this restriction. You could have like an odd number of variables and it would be fine. Here, I mean, you can always pad, and then I suspect if you worked out the details, you could probably show that like the padding is in some sense free, like it doesn't increase the prover work, but it would require maybe a little bit of modifications to the protocol, or at least more exposition. But yeah, to answer your question, if you have a column that's of size 2 to the n, you have n variables.
Okay, but so with your example of 20, so you divide first in 2, but after that you've got 10. You divide again in 2, but after that you've got 5. What happens then? Do you do like another factor, like the factor 5? Or...
No,
my it was always like a power of 2 that you would use in terms of variables, like 16 variables. And so you've got a domain of 2 to the 16. So it's exactly what we have on our side. We have 2 to the 16 as a base, and 15 variables. And so we didn't know if other projects were doing others.
We only in Mercury we only fold once, so like we only need an even number of variables, not a power of 2. Yeah.
Oh, okay. I thought it was like okay. I got then.
Yeah, and then in Gemini they would fold like 20 times.
Okay.
I guess Liam, that was the question. So Danny was asking more like in general, if you have 20 variables, you were mentioning that some projects folded the factor 4, for example. So what would be the approximate numbers? So, but I guess 20 and 4 for Gemini is one answer, and then for Mercury it's just 2, and so it needs to be even.
Mm-hmm.
And was it trade-off? So like why would you not fold more? What's the trade-off if you have like Gemini and you have 20 variables as you mentioned? Why don't you fold by like 5 or 10?
Well, I mean, in some sense, that's what Mercury is. I think that if you were in like without this sort of O of one size folding step, it would require sending more information. So if you, I think the naive construction of Gemini with a higher degree folding factor, you'd send more data, and so if you fold by a factor of 4, you'd be sending 16 evaluations instead of 2, which would, increase your proof size.
Yeah, I was actually wondering. Sorry, Danny. Do you have another question or?
Yes.
Yeah.
It's totally different on a different subject, so I don't know if your questions.
Okay, let me ask a small question first then. Okay, so my question would be, so Liam, can you imagine the same protocol like Mercury being presented in the same way, but with a variable number of folding rounds, where you reduce every time you fold? So like a Gemini basically with the modular reduction at every step. Would that be of any use at all?
I think in the case of KZG, it would work. I don't think it would be very useful because with 2 rounds, you already get kind of the best you can do, right? Like the prover work is dominated by an MSM of length n, and even if you folded, say, in 3 rounds by cube root n or something like that, it would still be down. You still have the same amount of MSMs approximately. You'd be moving from like 2n plus O of square root n to like 2n plus O of cube root n. So it'd be like very slightly less MSM work, but not enough to affect the running time of the protocol much.
Yeah, I think I see what you mean. Yeah, thank you. Danny, do you want to ask?
Yeah. So I don't know if it's I don't know if it's more. It's a question on if it has been explored before, but like on slide 8, is mostly about the isomorphism that is used between the multivariate polynomials and the univariate polynomials. It's like the natural transformation between the two vector spaces. I saw it was in Zeromorph. I don't know if it's Gemini who introduced it before, but it's like a natural transformation. And I was wondering if it makes sense also to try to have another transformation than this one. I've never spent more time on this. Just wondering if there is other transformation that have been explored, like might be stupid, but like in part of, depending on the circuit, you've got like a pre-processing phase that gives another mapping. Might be stupid, but yeah.
No, I don't think it's stupid. It's a good question. I mean, so for what it's worth, it's not in the paper, but I have a version of Mercury that works with the like Lagrange basis. So if you replace this, like suppose we just called the sum of the bits with powers of 2 like n, or then like this is like x to the n. I have a version of Mercury that has slightly worse constants but the same asymptotics that works with f hat of b times like the nth Lagrange at x. And if for some reason you wanted to combine this with a protocol that like already used or for some reason required commitments in Lagrange base, like I don't know, say Planck or something, that would that would be nice. Besides Lagrange and what I would call like monomial base, you could ask for like an ECFFT basis or something like that, or like a Circle-Starks type basis where like your evaluation points are in a quadratic extension. But I don't know. Yeah, it's an interesting question to ask if other bases would be interesting.
Yeah, because there are many other bases that we never explore, I think, in different papers. Mostly we always use the same encoding or the natural encoding. When I say natural, is the one we would use by default. I don't know if canonical is the right word, but yeah. I've always been thinking, trying to do something else. Okay.
Yeah, no, I think it's a good like direction to explore. I mean, there's just the monomial or the canonical one, which is nice because right, it has the tensor decomposition and all of that. And then there's also like these kind of evaluation domains with the Lagranges. But beyond that, I actually can't think of any protocols off the top of my head that use anything besides that. So maybe interesting.
I suggest, Marek, you ask a question, then we wrap up because we're 18 minutes afterwards.
Okay, thank you. It's a very quick one. So your result is now you achieve constant proof size and also linear prover. So do I understand correctly? This basically implies for snarks that all the previous snarks that use MLPCS and had a linear prover time, that probably something like log squared of n like proof size, and now this would enable to keep the prover efficient, but only then have log n proof size using Mercury instead of these other MLPCS schemes that
I think that the existing univariate, or not univariate, the existing sum check based like KZG snarks have log sized proofs. Basically, you do sum check, which typically will have a log sized proof. And then you'd use like a Gemini at the end. So you'd have like log rounds for the sum check, and then you'd have log size for Gemini.
Okay, so it's sequential. Yeah, okay, get it. Because this final step of sum check is actually where you need the. Yeah, okay, I think I see it. Sorry, because yeah, thanks for clearing that up for me.
Yeah, and if I just a final note, the big benefit So calling a constant size, I think this is a good point, that like the overall snark is almost certainly not constant size. If you're doing sum check, it's going to be log size. However, verifying sum check by itself only requires field operations, like the checking the univariate evaluations, agree, and so on. Verifying Gemini takes log n, like scalar multiplications from the verifier. Verifying Mercury only requires a constant amount of verifier work. So for on-chain verification on like Ethereum or something, verifying Mercury, I haven't actually done it, but I can't see why, and I strongly suspect that it would be a lot cheaper than evaluating Gemini, because you don't have to do log scalar moles, you'd only do 0.1 scalar moles. So really the constant proof size is probably better conceptualized as like constant verifier work, or constant verifier cryptographic work.
Okay, thanks for the explanation.
Okay, I will take this as the last question. Thanks everyone for coming. Thanks particularly Liam for coming, giving the talk, and for staying with us for 15 more minutes. And yeah, thanks everyone, and see you at the next episode of this. Ciao, have a nice day.